Welcome, everyone. Today we're jumping into a brand new explainer all about something that literally structures our entire reality, and that is the mathematical connections all around us. I mean, think about it. We interact with thousands of variables every single day, right? Time, money, distance, temperature. But how exactly do these variables interact with each other? How do they connect? Well, that's exactly what we're going to unpack today by looking at the fascinating world of mathematical relations and functions.
I want you to start off by just thinking about this question for a second. Can we mathematically predict the world? Or more specifically, can cause and effect always be perfectly predicted? Like, if I change one variable, am I always going to know exactly what happens to the other one? Well, as you'll see, the answer actually isn't always a simple yes. Sometimes things are highly predictable, for sure, and other times, well, they're kind of messy. And that beautifully sets up our entire purpose today, which is understanding the absolutely critical difference between a mathematical relation and a mathematical function.
Okay, let's dive right into this. Here's our roadmap for the explainer today. We're going to cover the math of connections, properties of relations, the exclusive function club, the vertical line test, and finally, mapping domain and range.
Section 1. The math of connections.
So basically, everything in math starts as a set, which is really just a collection of objects. And when we pair every single element of set A with set B, we get what's called a Cartesian product. Now, from that massive pool of pairs, we get our first major concept, a relation. Simply put, a relation is just a connection between two quantities. Formally, it's a subset of that Cartesian product. But honestly, you can just think of relations as basic cause and effect relationships. You put an input in, and you get an output out. For example, as the temperature drops outside, the number of ice patches on the road goes up. That connection right there, that's a relation.
Let's look at a real-world example. Imagine you're buying fabric swatches. On sale day, the store says, hey, 3 swatches for $4. But wait, that means if you spend $4, you might be buying 1, 2, or 3 swatches, depending on what you pick. Your input, the $4, has multiple possible outputs. It's a many-to-many relation, and let's be honest, its relationship status is basically it's complicated. But on a regular day, swatches are just a flat $2 each. So if you spend $4, you are absolutely getting exactly 2 swatches. No guessing. That is a solid, reliable, one-to-one relation.
Section 2. Properties of relations. Now, mathematicians categorize these relations based on certain key properties: reflexive, symmetric, antisymmetric, and transitive. Let's use a family tree to kind of make sense of this, specifically looking at the transitive property. Think about it like this. If person X is an ancestor of person Y, and person Y is an ancestor of person Z, then naturally, person X is an ancestor of person Z. That relationship is beautifully transitive. But what about is a parent of? Well, if X is the parent of Y, and Y is the parent of Z, X is definitely not the parent of Z, right? X is the grandparent. So the parent relation is absolutely not transitive. And as a quick side note, when a relation actually manages to be reflexive, symmetric, and transitive all at once, it reaches this really special status called an equivalence relation.
Section 3. The exclusive function club.
Welcome to the exclusive function club. So the crucial point here is this exact quote, is a function of means is determined by. A relation only gets to be called a function if every single input has one and literally only one unique output. True functions require absolute, unwavering predictability. There's no way around it. You simply cannot have a single input pointing to 2 totally different outcomes. It must be perfectly determined.
Let's contrast a couple of scenarios to make this crystal clear. Think about cutting a pizza. The number of cuts you make across that pizza is going to yield a highly predictable exact number of slices. One input, one definitive output. That is a true function. But contrast that with tracking worker output at a factory. Let's say your input is 2 workers on a shift. Well, sometimes those 2 workers produce 4 units, and other times those exact same 2 workers might produce 7 units. Because that one input, 2 workers, can yield sporadic, completely different outputs, it is just a relation. It definitely doesn't make it past the velvet rope into the exclusive function club.
Section 4. The vertical line test.
Enter the vertical line test. You can really think of the vertical line test as the actual bouncer for the function club. So on this graph, we see a beautiful U-shaped curve, which is called a parabola. If you take a perfectly straight vertical line and sweep it across the graph from left to right, it should only ever touch the drawn curve at exactly one point at any given time. If that vertical line touches the graph in 2 or more places simultaneously, it means one input on the x-axis has somehow snuck in multiple outputs on the y-axis. But as we can see with this particular curve, the bouncer is totally happy. The line only touches once. So this relation is indeed a function.
Section 5. Mapping domain and range.
Once we know we have a true function, we have to establish its territory. You can think of domain and range as the velvet ropes defining the exact boundaries of where our function actually exists in the mathematical universe. The definitions are incredibly succinct. The domain is simply the set of all possible input values. These are your x values, the numbers you are legally allowed to feed into the equation. The range, on the other hand, is the set of all possible output values, your y values, the actual results that come out after all the math happens. So, inputs going in, outputs coming out. Simple as that.
Now, finding the domain isn't always just a free-for-all where it's any number in the world. There are two golden mathematical rules we absolutely must follow when figuring out our domain. First, if you have a fraction, the denominator cannot be 0. You literally cannot divide by 0. It essentially breaks the mathematical universe. Second, if you're dealing with an even root, like a square root, the stuff under the root, which is called the radicand, must be greater than or equal to 0. Why? Because you can't take the square root of a negative number and get a real result.
To make this perfectly actionable for literally any problem you might face, just break it down into these two simple steps to map your function. Step 1. Set the bottom of any fraction so it does not equal 0, and then just solve for x. Step 2. Set the inside of any even root to be greater than or equal to 0, and solve for x. By doing this, you're explicitly drawing the borders of your domain. You're finding out exactly which inputs are legally allowed into the function club.
And this brilliantly illustrates why knowing your domain is so incredibly important when we look at the actual graphs. On the left, we have a continuous domain curve. Notice how it sweeps smoothly across the x-axis? There are absolutely no mathematical roadblocks. Every input works perfectly. But on the right side, look at that heavily discontinuous broken graph. You have a solid curve that suddenly just stops, an empty gap, and then a straight line starting up somewhere else completely. That broken space represents the exact numbers that were restricted by our domain rules. So the domain actually dictates the physical shape of the function on the page.
We've covered a whole lot of ground today, from broad Cartesian products all the way to the highly exclusive rules of functions and their domains. But I want to leave you with a thought that takes this off the graph paper and into the real world. Take a look at the variables in your own life right now. Whether you're tracking your personal finances, your time management, or your daily habits, are the actions you're taking behaving like a strict, highly predictable mathematical function where you know exactly what the output is going to be? Or are you operating in a messy, complicated, totally unpredictable relation? Because, just like in math, the more we understand the rules connecting our inputs to our outputs, the better we can predict and actually design our results. Thank you so much for exploring the math of connections with me today.